Okay, we move on to our final stage. Reporter is now from Singapore. You have 5 minutes preparation time. Good luck, and you may begin.
Testing. Can I begin?
Yes, you can.
Right. Good morning, judges, opponent, and reviewer. I'm Jin Ming from Singapore, and today I'll present question 13, magnetic pendulum. So first we see from a question statement that we're supposed to make a light pendulum with a small magnet attached to its free end, and this is hung above an AC electromagnet of much higher frequency. Through literature review, we know that this is also commonly referred to as the Dubuschinsky's pendulum. This pendulum exhibits undamped stable oscillations, and we're supposed to investigate this phenomenon. So first, let's compare between the magnetic pendulum and the conventional driven pendulum. We can see some major differences. The first difference is that in the magnetic pendulum, there is no resonance involved because the AC frequency is so much higher than the natural frequency of the pendulum. And secondly, for the magnetic pendulum, there's a discrete stable amplitude spectrum, whereas for a conventional pendulum, there's only one single stable amplitude. So we know from the question statement that we're supposed to focus on the undamped oscillations of this pendulum, and therefore we shall focus our research on three fundamental questions. Firstly, how are these stable oscillations reached? Secondly, why are these stable amplitudes discrete? And thirdly, what amplitudes are stable? So here's the content for today. First, I'll go through our experimental setup and the phenomenon of the magnetic pendulum, and then I'll move on to a qualitative theory. We'll then move on to a quantitative theory to predict these stable amplitudes, and lastly, we'll compare our theory and our experimental results. So here we see a picture of our experimental setup. We can see our light pendulum and a small magnet attached to its free end, and an AC electromagnet below it. We use an oscilloscope to check that our AC waveform is not distorted. To power our electromagnet, we connected a power amplifier to a function generator, and we use multimeters to measure the current and voltage through our setup. And to release our pendulum, we cut the light string attached to our pendulum, and this can be detected using a photogate sensor. We record all motion of a pendulum with a high-speed camera at 480 frames per second, and we employ frame-by-frame pixel counting techniques to track our pendulum over time. Now we note that once we release our pendulum, there could be an initial AC phase which is non-zero, and we can measure this initial AC phase through the use of a data logger connected to a photogate sensor and a voltage sensor. This initial AC phase is a key parameter that will be investigated later on. So in our experiments, we observe a total of two types of pendulum behaviors. The first behavior is the convergence towards stable amplitudes, and the second behavior is a straightforward decay of the pendulum, as shown by the rapid decrease of amplitude against time. We will now move on to a qualitative theory to explain these stable amplitudes and to explain why they are of discrete nature. So we note that as our pendulum swings, it loses energy due to kinetic friction and air drag, and it must gain energy on a regular basis from the electromagnet to maintain stable amplitudes. However, it is unclear how this energy exchange takes place without resonance. We note furthermore that as a pendulum swings, there's a very narrow interaction zone in which the majority of the interaction occurs, and outside this interaction zone, there is almost zero driving force. And therefore, we conclude that the force angle graph on our pendulum is shaped like a spike. This spike function is oscillating through time because our electromagnet is powered by an AC source. By doing a time trace of this force angle graph, we're able to obtain the following force time graph of our pendulum. We will now analyze a single half cycle of our pendulum. In this graph, a positive force will accelerate our pendulum, whereas a negative force will decelerate our pendulum. The blue line here indicates the minimum amount of impulse that must be gained to counteract damping effects. We note that in this first half cycle, the amount of impulse gained above the blue line is greater than the amount of impulse lost below the blue line, and therefore momentum is gained in the first half cycle. We note that for a large angle pendulum, increasing amplitude will lead to increased period, and therefore we conclude that the next time of interaction will be delayed, and the next duration of interaction will be shortened because the pendulum now moves faster. Now, if in the second half cycle, the pendulum loses momentum, then this will correspond to a negative feedback scenario. Of course, it is also possible for the pendulum to first lose momentum in the first half cycle and then gain momentum later on. These two scenarios correspond to negative feedback and are conducive for the convergence towards stable amplitudes because it allows the pendulum to self-regulate energy exchange. It is also possible for the pendulum to continue gaining momentum or continue losing momentum over multiple half cycles, and these scenarios correspond to positive feedback. This will correspond to the uncontrolled amplitude gain or uncontrolled decay of the pendulum. We can verify that this feedback mechanism does exist in our setup by measuring the AC phase every time our pendulum enters the interaction zone. So here we see a plot of the measured AC phase at entry points against time. And we see that there's initially an erratic region, but afterwards, the AC phases tend to converge towards a single stable value. And this coincides with the attainment of stable amplitudes on our pendulum. This is very strong evidence that the negative feedback mechanism is indeed at work and is pushing our pendulum towards stable synchronization with the AC source. We note, moreover, that in the decay scenario, the AC phase at entry appears erratic and random. And this indicates that the failure to establish negative feedback mechanism is the main reason for the failure to establish stable amplitudes. Now that we have fully explained the time evolution mechanism of our pendulum, we can go on to explain why these stable amplitudes are of discrete nature. So first we recall the energy condition that at stable amplitudes, the momentum gained in each half cycle must be equivalent to momentum lost due to damping effects. Now we note that for a sustained increase in momentum in every half cycle, the AC phase at times of entry into the interaction zone must be exactly opposite that of the preceding half cycle. This is because in between each half cycle, the pendulum has changed direction, and therefore the forces must change direction to continue accelerating our pendulum. This allows us to conclude that the pendulum period must be an odd multiple of the AC period. And since we now have a discrete set of stable frequencies for the pendulum, we will naturally have a discrete set of stable amplitudes, because for a pendulum, the frequency and the amplitude are related. Now we conclude that there are four main parameters that will affect the time evolution of our pendulum, namely AC frequency, AC current, pendulum length, and AC initial phase. We will explore these parameters in our theory later on. We will now move on to a quantitative theory to predict these stable amplitudes. We will start with Newton's second law for torque for the simple ideal pendulum, and we write the law as follows. This relates the angular acceleration of the pendulum to the restoring torque due to its weight. To account for damping effects, we add in the following terms for air drag and kinetic friction, and we also add in the following driving force term, which is a position-dependent, time-varying function. To obtain the form of the driving force function, we need to model our electromagnet and the permanent magnet. For the electromagnet, we integrate Biot-Savart's law across our geometry to obtain the overall magnetic field produced. And for our permanent magnet, we model it as a current cylinder, where we integrate the force on a small current-carrying element over our cylindrical geometry to obtain the following expression for the driving force on our pendulum. This expression contains a parameter A that corresponds to surface current magnitude. We can characterize this parameter by measuring the magnetic field strength of a magnet using a digital Hall probe. And we fit the following graphs of magnetic field strength against distance to obtain a best fit value of A close to 14,000 amperes. By using this value of surface current magnitude, we're able to obtain the flowing graph of driving force against angle, and this corresponds to the characteristic spike-shaped function that we qualitatively understand. We know that we can characterize the air drag coefficient by numerically solving for an unpowered decay of the pendulum and fitting this decay to our data from experiments. And through this, we are able to obtain the following values of air drag coefficient and kinetic friction coefficient. We can now solve numerically for the equation of motion and obtain the following predicted angular displacement time graph of a pendulum and a corresponding phase portrait. We overlay our data, which is in red, and we see a very close fit between our data and our theory. We note that near angles of 0, there's a general disturbance on our pendulum, and this corresponds to the accelerating or decelerating effect of an electromagnet on our pendulum. We can now check the stability of each of our solutions, and this allows us to obtain the following plot of stable amplitude against AC frequency. Now, to read this complicated graph, we can pick some AC frequency of interest, for instance, 40 Hz, and plot the vertical line at that AC frequency. The points of intersection between the vertical line and the curved theory lines will give us the stable amplitudes at that AC frequency. We can overlay our data, and we see a very close fit between our theory and experiment. There are two main deductions to be drawn here. The first deduction is that as we increase the AC frequency, the number of stable amplitudes seem to increase. This is explained by the fact that at increased AC frequency, there's increased opportunity for the pendulum to establish negative feedback over a wider range of pendulum frequencies. And as we move up the graph, the density of stable amplitudes seem to increase. This is because as the amplitude of a pendulum increases, its period increases more and more sharply. We can repeat this calculation for another pendulum length, in this case 34 centimeters, and we see a very close fit between our data and our theory. And again, for the 46 centimeter pendulum, a very close fit between theory and experiment. Now, comparing these two phase portraits of very similar initial conditions, we see that they approach different stable orbits, which correspond to different stable amplitudes. This is because the AC initial phase for these two phase portraits are different. And this illustrates the fact that the AC initial phase is a key parameter that can affect the evolution of a pendulum greatly. We can plot the following color plot of AC frequency against AC initial phase. And on this color plot, each pixel color corresponds to the final stable amplitude that's predicted by our theory. This is given by the color scale above. And the black regions indicate pendulum decay. Now we can see that as we increase the AC frequency, the amount of black regions seem to increase. And this can be explained by the fact that at increased AC frequency, in each half cycle, the amount of momentum gain is reduced because there's a greater cancellation effect between the positive forces and the negative forces. This means that at increased AC frequency, there's lower tendency for the pendulum to converge towards stable amplitudes that require higher energies. We can take 2D cross-sections of this color plot and obtain the following plots of stable amplitudes against AC initial phase. And we see a very close fit between our theory and our experiments. The step-like functions shown here show clearly the discrete nature of our stable amplitudes. We can repeat this calculation for another pendulum length, in this case 46 centimeters. And we again see a very close fit between our experiment and theory for the stable amplitude AC initial phase plots. Now in conclusion, I went through firstly our experiments and described how I was able to vary pendulum length, AC frequency, and AC initial phase. I went through a qualitative theory in which I explained for the presence of these stable amplitudes through a negative feedback mechanism. And I also went through a quantitative theory to predict these stable amplitudes very accurately across numerous parameters. In conclusion, I believe I fully answered this question. However, our research does raise some additional questions about the possibility of chaotic behavior. We note that the equation of motion for our pendulum resembles very closely the equation of motion for a conventional driven pendulum, which we know is chaotic in nature. The difference between these two equations of motion is a driving force term. And therefore, it is very natural to ask a question about whether chaos is present in our system. As of now, we do not have sufficient data to prove or disprove the presence of chaotic behavior. And this is a very interesting open-ended question for future research. Here are my references, and thank you for your time.
Thank you very much, and we move straight on to questions from the opponent.
Thank you. Thank you for the reporter. It's a very impressive presentation. And okay, I want to ask you something. First, you say your magnetic field distribution is like this. Your solenoid is this thing is your coil, and your magnetic field is like this one.
Yes, and the pendulum would be here.
Is this one?
Yes.
So this is N, this is I.
Yes.
So at the very center point, how does it get force? Or is this force exist or equals to 0?
Indeed, the force experienced by the magnet is peak, the maxima at the center point.
So you find that this tangential, this direction of tangential is this point. So this is the B. And this is vertical.
Yes.
This is horizontal, this is vertical, this is N and S. So how does this has the, you say the force is like this one?
This is a very interesting question, but I think we need more time to discuss this, so perhaps we could discuss this during the discussion later on.
And
clarification questions.
Okay, and the next question is, what do you think it will affect the negative and positive feedback?
The significance of those?
Yes.
Negative feedback allows our pendulum to self-regulate and therefore converge towards stable amplitudes. Positive feedback will make it decay, and therefore that corresponds to the decay scenarios.
And what's the nature of the various amplitude? The nature, not the mathematical equations.
They are discrete. They are of discrete nature. So, so they are of discrete nature. They are discrete. It means that they have well-defined values. It's not a continuous curve.
Okay, thank you. Testing. Okay, ladies and gentlemen, I am just Hong Guanghe from the team of China, and I'm obviously the opponent for the 13 magnetic pendulum. First, I want to thank the reporter has a very impressive presentation and consider a lot of things Let's begin with the problem review. The key characteristic of this pendulum is high frequency, undamped, and various amplitudes. And our task is to study and explain the phenomenon. And let's review of the presentation. First, it has a very clear-cut problem understanding, and the experiment setup is very precise, and it has a qualitatively count and a quantitatively account. But these two things are not so relevant, and the model verification is done very well. And about the problem understanding, he fully explained the problem and noticed that there are damped oscillation and high frequencies and various amplitudes requirements. And the theory, the strong point is it has an evaluation regulation mechanism explanation in qualitatively and the numerical solutions to describe the amplitudes. And the weak point is he didn't explain the physics nature of the various amplitude. And the experiment, it has a very precise setups. And the weak point is he does not measure the damping coefficient, which I think is a relevant parameter to this pendulum, and didn't investigate low and high frequency, because we believe that if you change the frequency of the AC supply from a low frequency to a high frequency, there must be some change or some other phenomena or relationships. So I didn't see that in the report. And here is the discussion we want to discuss. First, the very nature of this pendulum, why does it can have an undamped oscillation, is because the phase of the interaction and the time interval between two consecutive entries into the interaction zone. And the nature of the various amplitudes I want to discuss later. And as the frequency increases, the reporter says that there will be more stable amplitudes will be. So is there a range of frequency required to reach the undamped oscillation? And I want to move to the discussion part. Yes. And the first thing is, the coefficient of the damping oscillation.
Yes, I characterized it empirically through measuring the decay envelope of our pendulum.
Yes.
So I solved numerically for the decay envelope from our equation of motion, and we fitted it to the